When a projectile is launched at an angle and has different starting and ending elevations, the analysis is not necessarily significantly more difficult, but you do have to keep track of a few key concepts, and there's one or two pitfalls that students usually tend to misperceive. So I'm going to try and clarify that in this video. So just to show you an example, this would be an example of something that's launched at an angle with different starting and ending elevations. I don't know, a ball is kicked or the missile is launched at some kind of angle, so it's not going horizontal. Some kind of angle follows its parabolic path, gravity is the only thing acting on, etc., until it hits the ground. This is only one of the examples. I could also launch it from down here and have it land up here. As long as I have different starting and ending elevations, it will not matter whether the object is rising up and ending above where it started or whether it's falling and ending somewhere below where it started, as can be seen in this picture. So a few of the key concepts, and some of this will certainly be right in line with things we've discussed, and hopefully some of this is common sense at this point. But the first one, the object lands below its starting elevation, something like this example up here. The total delta y that it's experienced, because it's actually ending up below where it started, is going to be negative. If it's the reverse and something is launched from, say, down here and is launched and lands up here, well, that object ends above where it started, so the delta y, the displacement vertically that it experienced, would be positive. So hopefully it seems kind of straightforward, but just keep in the back of your mind, delta y will be negative if the object winds up below where it began, and delta y will be positive if the object lands above where it began. The last one, and this is something that you probably know already, the y velocity will be 0 at the peak. So as I launch this here, at this peak right here, the y velocity will be 0. It's the moment where it stops for a split second as it's turning around and then travels in the other direction. So it was originally traveling up, stopped, and then started traveling down. That's hopefully a concept that is ingrained in your mind at this point, but just keep it in the back of your mind just to be safe. Common student errors. Here are the two most common things that I see, and it makes complete sense. That's why they're common errors. The first one is stating that the initial y velocity and the final y velocity are equal and opposite. Well, that only applies if they have the same starting and ending elevations. If you look up here, this doesn't have the symmetry that starting and ending at the same elevation did. If I had launched from here and it went up and then down, it's pretty symmetrical. That's why we get these relationships like the y velocity is equal and opposite. But if I launch it up here, we're ending at a different elevation. This first half of the motion right here is a little bit different than this half. There's a lot more time over here. So because of this additional time, the additional change in y, you can't just say that everything's going to be even and you're going to get an equal and opposite relationship. So that is true, certainly, for the same starting and ending elevations, but please do not think that that is also true for this case. That's only true for a very symmetrical projectile launch, which you only see when you start and end at the same elevation. Likewise, saying that the time to the peak is half of the total time, that only applies with one of those symmetrical launches. If you see here, the peak is not at the middle of this motion. It's actually closer, it looks like maybe to the first third of the motion. When you lose the symmetry that you have from beginning and ending at the same elevation, these two concepts do not apply. Please put these in your notes somewhere. They're very, very common errors. And again, it makes sense because it's very hard typically to keep track of which concepts apply to which type of projectile launch, etc. The easier thing is to just try and understand from the diagram, try and understand from the concepts that, well, half the time will not get you to the peak because this clearly is not halfway through the motion. So if you can kind of pick up on things like that, it'll probably be a little bit easier as time goes by. I'd like to jump right into an example because it's really not that different. I just want to show you the slight differences. Here's a very, very, very traditional problem. You have an object that's located on some kind of cliff that's 80 meters high. It's launched with a velocity of 7 meters per second at an angle of 35 degrees. Now this is not the initial x or y, this is that combined velocity. So the two most common questions, how long will the object be in the air? That object will launch in this direction and then fall to Earth or the ground, whatever planet you're on. And how far from the base of this cliff, how far will it travel horizontally when it hits the ground? Probably your two most common types of questions. So if we look at the first one, part A, how long will the object be in the air? I want to find time. So what I did was I started with finding the initial velocities like we've done in the past. I've drawn my combined velocity, my 7 meters per second at a 35-degree angle. And hopefully at this point we realize that some of that 7 meters per second will be the forward x velocity, and some of that will be the upwards y velocity. And just using SOHCAHTOA and trigonometry, I haven't written out every step, I've just shown the final step. My initial y is going to be equal to 7 times the sine of 35, which gives me 4.01 meters per second up, which I've recorded over here. And my initial x velocity will be 7 cosine of 35, which equals 5.73 meters per second to the right, which I've written here and here. These are the same because there's no acceleration for a projectile on the x. My acceleration on the y, since we're on Earth, is always negative 9.81 meters per second squared. And delta y, if you think back to what we said previously, if the object lands below its starting elevation, delta y will be negative. That's exactly my case here. This object, despite being kicked up into the air, it starts here, it ends here, it displaces negative 80 meters in the y direction. Now there's a note here. I say be careful because you will run into a problem with angled projectiles that do not begin and end at the same elevation. And rather than just explain it, I've actually started to do an equation which seems like it'll work. I chose this kinematic equation, plugged in all of my known variables, and the problem I ran into is that I have a delta t here and a delta t squared here. Now the only way to solve a problem where you have like an x and an x squared would be to use the quadratic formula. And that is certainly a way to solve this problem. I don't always recommend it because you have to look up the quadratic formula or you have to use a graphing calculator. And if you plug in the wrong variable or you don't square what you need to square, it can get a little bit tricky. I'm going to show you an alternative method, but I do want to highlight if you'd like to use the quadratic formula for this question, you will certainly find the correct answer. I usually choose instead to do the alternative. What I like to do is I ran into this problem because I chose the one equation that did not have final velocity here, as we've kind of been trained to do so. That will work using the quadratic formula. A way to go around having to use the quadratic formula is to go back and find that missing variable, and that'll open up the other kinematic equations, which you can then use to much more easily find change in time. And that's what I've done here. I've used the equation for the final velocity, and I've set it equal to initial velocity squared plus 2a delta y. And when I plug in my known values, I wind up finding that the final velocity is negative 39.82. So now that I have this fourth variable, it opens up the equations I can use, and I just use this simple one right here. And plugging in what I know, negative 39.82, which I found in the previous step, equals, and I've completely forgotten to put this term in here, so this will be VIY, so this should not be 3, this should be 5.73. I apologize for that. This whole term here should be 5.73 plus negative 9.81 times delta t. If I plug in 5.73 here, and then I solve that out, I will find that the time that this projectile is in the air, from the time it is launched from this point to traveling up to its peak and then falling back down, will be a total time of 4.47 seconds, which I can then write on both the x and the y sides. That's exactly what I've done here. But point B is asking how far will it travel. I've replaced all the values, including my calculated y velocity and my time, and I've just picked a kinematic equation that will work for me. I like this one because the acceleration in the x is 0, and this whole second term will cancel out, and I'm left with delta x equals vi x delta t. So my delta x will equal 5.73, my initial x velocity, times my change in time, 4.47. And that will give me a total displacement in the horizontal direction of 25.6 meters.